Let's see a DHCP example. There's a newly joined-in laptop wants to get the internet connection. And before this laptop can really connect with the internet, it requires three informations. One is the IP address. The second one is the IP address of the gateway router. And the third information is the IP address of the DNS server. And all these three informations can be getted from the DHCP server. Then this laptop will prepare a DHCP request, which will be encapsulated in a UDP segment, and then combined with the IP header to get an IP datagram, and finally combined with link layer header to get a frame, then ready to send it out. Then the laptop will use a broadcast way through this destination IP address, which is OF on the local area network. And when this Ethernet frame received by the router running the DHCP server, or by the way here, usually the DHCP router will sticking with the routers, or they will combine together. So when the DHCP request received by this DHCP server, it will deliver all the way up to the application layer of this DHCP server. Then the DHCP server receive this request. It will prepare a DHCP ACK message, which contain these three informations, which are clients, which is usable IP address for this client, and IP address of the gateway router, or we usually will call it the first hop router, and also name and the IP address of a DNS server. Then still go through the hierarchy, or go through this each layers, and all the way down to the physical layer, send this DHCP ACK message out and to the DHCP client. So when the DHCP client or the laptop receive this DHCP ACK information message, it can get the IP address for it, and the name and the IP address of the DNS, sorry about that. Here is a DNS server, and also IP address of the gateway router. There's three informations, and then the laptop can use the service provided by the internet. So here we have a question. Probably you will ask, so how does the network get a subnet part of the IP address? The answer is gets allocated portion of its provider internet service provider's address space. So for example, here, this IP address has a block of, or this internet service provider has a block of IP address, which is this one. And from this IP address, we can see the subnet part is a 20-bit. It's all the way to here. So that means this IP address or this block can have 4096 IP addresses available under this domain, because from the subnet mask we will know the host part has 12 bits, and then this whole block will be divided into multiple portions. You can see here there are numbers of organizations, they can get an IP address block from this internet service providers. And for each organization, the subnet mask is a 23-bit. And from the difference we can see from this 20 compared with the 23, there are 3 bits different. So we will know these are 3 bits. If we convert it to a decimal number, which is equal to 8. So that means this whole block IP address provided by the internet service provider can be divided into 8 portions. And for each one, which can support 512 IP address, because the host part for each organization is 9-bit. 9-bit. After you do a calculation, you will know it can support 512 IP addresses. Then we get another question. So we know the organizations, they can get the IP block from the internet service provider. However, where the internet service provider can get the IP block from? So this is the question here. And the answer is from this organization, ICANN, which is shorted for the Internet Corporation for Assigned Names and Numbers. And also here is a URL for this organization. And this organization, it can provide 3 services. The first one is allocates the addresses. The second one is to manage the DNS. And the third one is to assign domain names and resolve disputes. Then let's see the NAT. The NAT is shorted for Network Address Translation. So I'm not sure if you guys realize that. So for each one of you guys in your home, you only get one IP address from your internet service provider, no matter it's AT&T or MetroCast. However, in your home, you can use multiple devices and just go through this single public IP address. The multiple devices can connect the internet through this unique public IP address. And also when you check the IP address of each devices, and you will see that IP address is very different from the IP address or the public IP address provided by your internet service provider. So I'm not sure if you guys realize that these things actually how you can achieve through using only a single one public IP address to support multiple devices, the internet surfing services. Actually, is supported by the network address translation function. And also this function is provided by your the routers in your home. So all the datagrams leaving local network have the same single source NAT IP address, which is the public IP address we just mentioned. So in this case, is this one, which is a different source, and also with a different source port numbers. And then the datagrams with the source or destination in this network will have this kind of IP address for source and the destination. For your each devices, you will have this type of IP addresses, which is much different from this public IP address. But in your home may not be exactly like this one. And in your home, it's very possible you have this kind of IP address. It's very possible in your home you have this kind of IP address. So 192.168.0. Or something here different. And for this kind of IP address domain, it can support 256 IP addresses, but usually the last one for this 256, the domain is from 0 to 255, and usually for this last one, 255, usually we don't use it because this one is used by broadcasting purpose. And then we may ask why we need a network address translation function. So the motivation is the local network used just one IP address as far as outside the world is concerned. So through this net function, we can achieve these things. The first one is a range of addresses not needed from the Internet service provider. Just one IP address for all devices in your home, because from the outside we only need one IP address. The second one is can change addresses of devices in local network without notifying outside the world. So if you want to change the IP address within your local network or within your home, you don't need to tell your internet service provider, okay, I just change the IP address for my iPad or for my laptop. You don't need to do that because the internet service provider, they will not realize, okay, you have this much of local IP addresses. The internet service provider only know, okay, I just assign a public IP address to this customer. So that's the only thing the internet service provider need to know. And the third one is can change internet service provider without changing addresses of devices in local network. For this one, if you feel the current internet service provider cannot provide a very distant internet services to you, so probably you just change another internet service provider. For example, Verizon, maybe they can provide a better internet connection. However, within your home, for each devices, you don't need to change your local IP addresses. You only need to change your public IP addresses. That's the only thing you need to do to change your internet service provider. And for the last one is devices inside the local network, not explicitly addressable or visible by outside world. So that means if you within a net function, and this device is using the net function, which is more secure because the outside only know your public IP address. It doesn't know this information is sent from which devices within the local network. And then how to implement net function? Actually, we needed to do two replacement and one remember. So for the two replacement is the, let's see the first one. The outgoing datagrams, we need to replace the source IP address and the port number of the every outgoing datagram to a net IP address with a new port number. And then the remote clients and the servers will respond using only this net IP address and port number, or this public IP address with combined with a new port number as a destination address. Another replacement is this one, because the second one, the incoming datagrams will replace NAT IP address with a new port number in destination fields of every incoming datagram with the corresponding source IP address and port number stored in this NAT table. Then for the third one, this remember is every source IP address port number to NAT IP address new port number translation pairs will be stored in the NAT translation table, which later we will show you guys an example, so you will know what we are talking about here. So how to implement this two replacement with one remember. Then let's see NAT example. So suppose this is a home network and the router has a public IP address, which is this one. And there are three devices connect with this home router. And also we can see within the home, the IP address is very different from the public IP address. With the IP address format, it looks like this. It's a 10.0.0.x and 24. So that means the last digit should be the host part, and for the first three digits or decimals should be the subnet part. And then this device send a information or send a datagram out to this destination IP address combined with this port number. And from this port number, we can know actually this device send website or web server request because the port number is a reserved port number. Before this datagram send it to the outside or to the internet, it will first go through the router first. So when the router receives this datagram, it will change the datagram source IP address from the local IP address and the port number to a public IP address and with another port number, and insert these pairs into the NAT translation table, which is here. Then the router will send this datagram to the internet or to its destination, which is the web server. So when the web server receives this datagram, it will send a response back. And for the response message, will with reversed or switched source IP address and the destination IP address. So you can see it from here. The source IP address and the destination IP address between the request message and the response message, they are switched. And when this response message received by this router, the router will first check the NAT translation table to see the record or to see the address pairs for this one, and then it found it here. Therefore, the NAT router will change the datagram destination address from this public IP address and with this port number to the local IP address with this port number. Then forward this response datagram finally back to this device. And through this way, the device within the local network can communicate with the outside um, web servers or other devices through the internet without any problem. Then let's continue to see the network address translation. And for each port number is a 16-bit field. So that means the public or the home router can allow this much of simultaneous connections to connect with outside or connect with the internet other devices. However, the network address translation function actually is a controversial. So why are we saying that? So let's see these three aspects. The first one, the routers should only process up to layer 3. However, we know when the datagram from device within the home send it to the router will replace the port number with another port number and also replace the local IP address into public IP address. So for the port number part, actually it belongs to the business of transport layer. However, the net function, which is the router, will touch the business on the transport layer, which is belongs to the second layer. Therefore, that's the first controversial we see from the um, net function. The second one violates the end-to-end argument is still because each datagram's IP address and the port number will be changed with the public IP address and the port number. So the net possibility must be taken into account by the application designers when they design an application because they don't know whether the customers or the service providers they will sit behind the net router. For example, here, suppose if we have a web server just sit behind the net router, so how can the normal customer know the IP address and the port number for this web server? Because these two informations will be replaced or will be changed by the net router. And the third one is address shortage. Should instead be solved by IPv6. So that means, as we know, the for the IPv4 IP address, the total domain is 4 billion IP addresses under the IPv4 version. However, since the devices for each person get more and more, you have your cell phone, you have an iPad, you also have a laptop and a desktop, and other devices may use the IP address. Therefore, the 4 billion IP addresses is not enough for nowadays. And then, that's another reason why the engineers, they design the net functions because the shortage of the IP addresses. Therefore, since right now we just continually switched from IPv4 to IPv6 because the IP address domain for IPv6 is large enough for every single devices can get a unique IP address. So if everybody uses IPv6,
we don't need the net function anymore. Then we have finished the IPv4 addressing. Then let's see the ICMP and the IPv6. First, let's see the ICMP. The ICMP is shorted for Internet Control Message Protocol, which is used by hosts and routers to communicate network level informations. And within this ICMP message, it can contain the error report, for example, the unreachable host or unreachable network, port number, or protocols. And also, it can do echo for the request or replies. Um, Probably you guys know the ping function within the terminal actually is based on the ICMP message and this echo function. Even though we know the ICMP belongs to the network layer, however, um, it is looks like just above the IP protocol or IP layer, because the ICMP message will be carried within the IP datagrams, just like the UDP segment or the TCP segment. And the ICMP message will contain the type, code, and also the first 8 bytes of the IP datagram, which causing the error. And on the right side, we can see here list numbers of examples of ICMP message. And for each type and code combinations, they represent different meanings. For example, the type 0 and code 0 will represent the echo replying, and 40 will represent the source quench and control not use, congestion control and not used, so etc. etc. And also let's see this trace route and ICMP. I'm not sure if you guys still remember the trace route program, which we already talked about in the previous chapters. So for this trace route program, is from the source all the way to its destination along the path, and for each router, the source device will send 3 probes and to measure the delay from each routers along the path, just like this. And the source will send a series of UDP segments to the destination. And for the first set has TTL equal to 1. In the previous slides, we have talked about the time to leave field. And within that field has a counter, or we call it a TTL counter. So when a datagram travel to router, the router will deduct this TTL counter by 1 until the TTL becomes to 0, or this datagram arrive its destination, it will stop. If the TTL becomes to 0, the router will discard it, because we don't want the datagram uh, due to the errors or some problems can travel within the network forever. So for the first set with a TTL equal to 1, when these 3 probes arrive this first router, the router will deduct this TTL counter by 1. Therefore, this 3 probes TTL will become to 0. Then this router will discard this 3 probes and send a response back to the original device. And for the second router, it will set the TTL will be set to equal to 2, etc., and so on and so forth. And also for each props, it will insert an unlikely port number, which later I will explain why uh, the traceroute programs or functions will insert an invalid port number to each props. Then, when the nth set of datagrams arrives to nth router, the router just discards the datagrams due to the TTL equal to 0 and send a source ICMP messages, which is with type 11 and code 0. And for this kind of ICMP messages, it will include name of a router and the IP address of this router. Then, when the ICMP messages arrives the original devices, so the original devices can calculate or measure the round trip time from that router. So, how to stopping this traceroute program or stop this mirroring? Here has a stopping criteria. So for the UDP segment, eventually will arrive at a destination host, and the destination will return the ICMP message, which is type 3 and combined with a code 3, which means the port unreachable. Do remember here, for each props we insert an unlikely port number or invalid port number. So that's the purpose. So for this kind of a situation, even though the destination receive that props because the port number is incorrect or invalid, it won't forward this segment or this datagram to the up layer because the port number unreachable problems. Therefore, the source device can ping or can send a traceroute props to any devices and at the same time won't bother that device because it for that props will be discarded by the destination and also discarded by the routers along the path. Finally, the source will stop to sending out the props to still measuring or keep tracking. Let's continue to see IPv6. So the initial motivation, as we already mentioned, the IPv4 IP address, due to the limited of IP address domain, it can only provide 4 billions of IP address, which is not enough for nowadays. Therefore, we the engineers they have the idea to grab a wide and a more IP address domain for the entire network. The additional motivation is the header format helps speed up the processing or forwarding because some field in the IPv4 header has been removed from the IPv4. So the IPv6 header will become more slim compared with the IPv4. And also the header changes can facilitate the quality of a service for the IPv6. And for each IPv6 datagram has a fixed length of a header, which is a 40 byte. And also the IPv6 datagram will remove the fragmentation function from IPv6. Then let's see the IPv6 datagram format. The first VER is still the version number, which is the IPv6. And for the second one, the PRI, which is a priority. It can identify the priority among datagrams in flow. So that means in the future, if you pay more money for your internet services, your datagrams can apply or assign a higher priority. So that means when the internet transfer the datagrams, it will based on the priority, and if you pay more money, you datagrams can be transferred first compared with others. So that means you can have even faster internet speed compared with um, other users. For the third one, the flow label is to identify datagrams in same flow. However, the concept of a flow is not well defined. So for this one, as we know, when we're using the IPv4, between the sender and the receiver, there are multiple paths. So the datagrams from the same sender can use a different path to transfer these datagrams to the destination. Therefore, if you're using a UDP protocol, these datagrams, then when they received by the receiver, can be out of order. However, if we use IPv6 uh, and also we assign a flow label, so these datagrams, they can use the same path to transfer from the sender to the receiver. Therefore, we can avoid the out of order problems, especially for the application of video or audio, this kind of applications. For the next header field, this one is to identify the upper layer protocols for data. For example, the TCP protocol or the UDP protocol used by the upper layer. And the hop limit is just the same as the TTL in the IPv4. And for the IP address, source IP address and the destination IP address for the IPv6 version, each one will occupy the 128 bits, this much of long. And the final part is the real data. And the payload length will be indicated by this field. And let's see other changes from the IPv4. So the checksum will be removed entirely to reduce the processing time at each hop. Because the transport layer and the link layer, both these two layers, they will implement a checksum. Therefore, if we still add a checksum into the network layer, it seems like a redundancy. Therefore, the IPv6 decided to remove the checksum field from the header part. And for the options, it's still allowed, but outside of the header, which is indicated by the next header field. And also the IPv6 will use the new version of ICMP message or ICMP protocol. For example, additional message types such as the packet too big, because as we know, the IPv6 will remove the fragmentation functions. Therefore, when the previous or the sender send a datagram is too large, the router will simply drop it off and also send a IC packet too big ICMP message back to the sender to notice the sender. Okay, you cannot um, you cannot send a too large packet over the IPv6 routers. And also the ICMPv6 allow the multicast group management functions. As we know, for the IPv4, it can only support unicast and broadcast. However, the ICMPv6 can allow multicast. Then let's see the transition from IPv4 to IPv6. As we know, so currently the ground truth is the entire internet, both using IPv4 and IPv6. For some routers, it's already updated to IPv6, but there still have a large amount of routers they are still using IPv4 because not all routers can be upgraded simultaneously because there is no flag days. So the flag days means for that day everybody don't use the internet because we want to upgrade our routers from IPv4 to IPv6. That's impossible. You cannot have that kind of day. And how will network operate with a mixed IPv4 and IPv6 routers? So the solution we have is we call it tunneling, which is the IPv6 datagram carried as a payload in IPv4 datagram among the IPv4 routers. So what's that mean? When the IPv6 datagram arrive, arrived at the IPv4 routers, the IPv4 router will treat this IPv6 datagram just as a segment and re-encapsulate this this IPv6 datagram just like this. And for the blue area is the original IPv6 datagram. So, and for this entire thing is the new IPv4 datagram. So this IPv4 router just insert IPv4 header here combined with this original IPv6 datagram um, to get a new IPv4 datagram, then send it through the IPv4 routers. Then let's see this tunneling. So the physical wheel is just like this. The A, B, E, F, they are IPv6 routers, and the C, D, they are IPv4 routers. And the logical wheel is just like this. So between the B and the E, they will treat the IPv4 routers just like IPv4 tunnel, which is connecting the IPv6 routers. So when the when there is an IPv6 datagram transferred between the IPv6 routers from A to B, there's no problem. When router B receives this datagram and the router B knows the next hop, which is router C is IPv4 router, then the router B will do re-encapsulate this original IPv6 datagram to get a new IPv4 datagram and transfer to next router, which is router C. Then when the router D forward this IPv4 datagram to router E, the router E just extract the original IPv6 datagram from this IPv4 datagram, then forward it to the next hop. So we have finished the internet protocols, and then let's see the routing algorithms.